Welcome everyone. Today, we will be diving into the fundamental concepts of the MCS 51, specifically exploring its internal architecture and memory organization. Let's outline our primary objectives for this session. We will be focusing on two main areas. First, understanding the internal architecture of the microcontroller, and second, examining its memory organization in detail. To begin, the MCS 51 is designed around the Harvard architecture. This means it explicitly distinguishes its program memory from its data memory. The way the microcontroller fetches instructions depends on the external access, or EA, pin. If the EA pin is grounded, all instructions are fetched strictly from the external program memory. However, if the EA pin is connected to logic high, the initial instruction fetches are performed from the internal program memory. If the program crosses the internal memory boundary, the processor will automatically continue fetching from the external program memory. The maximum size of the total program memory, which is the internal and external combined, is 64 KB. The 8051 series microcontrollers adopted a pipelined architecture. A pipelined setup is highly efficient because it allows the processor to fetch an instruction code during the decoding and execution time of its previous instructions. As a point of comparison, the Intel 8086 microprocessor is capable of storing 6 such advanced bytes, whereas the 8051 architecture fetches and stores only 1 byte of the next instruction's code in its pipeline. Ultimately, this pipeline architecture makes the processor faster. However, keep in mind that when instructions are not in sequence, such as during program branching, these prefetched codes are dumped or abandoned. To secure your code, the MCS 51 includes program lock bits. These bits are provided to avoid unwanted piracy. Once these bits are programmed or locked, the content of the internal program memory cannot be read from the device by an outside circuit. Note that if you are using external program memory, those program lock bits cannot be utilized. The only way to remove the lock is through a standard program memory erase operation, which unlocks the bits but also simultaneously erases the content of the internal program memory completely. Moving to data memory organization, the external data memory capacity mirrors the program memory with a maximum size of up to 64 KB. This 64 KB limit for data memory remains constant regardless of the amount of internal, on-chip data memory the device has. Speaking of internal memory, it varies by microcontroller series. The XX51 has 128 bytes, while both the XX52 and XX54 feature 256 bytes of internal data memory. The internal data memory of the 8051 is structured very specifically and is divided into 3 separate functional parts. We have the scratchpad area, which starts at address 30H and continues onwards. Next is the bit addressable area, occupying addresses 20H to 2FH. We have the register banks located from address 00H to 1FH. Let's look closer at the register banks. The lower part of the internal RAM accommodates 4 general-purpose register banks, which are designated as bank number 0, number 1, number 2 and number 3. Each of these banks contains 8 general-purpose registers, designated R0 up to R7. These registers are incredibly versatile. They can store data or operands during arithmetic and logical operations, and they can also be used as counters to count down. Having multiple banks helps facilitate faster interrupt servicing. However, out of the 4 banks, only one can be active at a time. Following a system reset, bank number 0 is selected as the default, but you can change this bank selection through the program status word or PSW. Additionally, registers R0 and R1 of the currently active bank may serve as data pointers for indirect addressing. If these spaces are not being used as registers, they can simply function as a general-purpose storage area. Directly above the register banks is the bit addressable area. These next 16 bytes, starting from address 20H up to 2FH, contain exactly 128 bits in total. What makes this section special is that each of these 128 bits has an individual bit address varying from 00H to 7FH. This area is expected to store bit variables for your application programs, and they are basically used to control motors or equipment that require single-bit control. If you don't need to use it for bit variable storage, any unused bytes in this area may also be used to store standard bite-sized information. The final segment is the scratch pad area. Everything from address 30H to the rest of the memory may be used for any general-purpose storage, and this includes the system stack. It's important to note that after a system reset, the stack pointer, SP, is initialized at 07H, which means the stack itself starts from 08H onwards. In XX51 devices, the highest address for this scratchpad area is 7FH. For the XX52 and XX54 models, the highest address extends up to FFH because they boast a larger on-chip RAM size of 256 bytes. Additionally, any unused bytes from the bit addressable area or the register banks can also function as general-purpose data storage. Now let's talk about the heartbeat of the system clock. The external crystal is connected between pins number 18 and 19 on the microcontroller. The setup depends slightly on your device type. For a CMOS type device, the external clock signal must be supplied at XTL1, which is pin 19, while the XTL2 input on pin 18 must be left unconnected. For an MCS type device, it's reversed. The external clock signal is supplied to XTL2 on pin 18, and the XTL1 input on pin 19 must be grounded. The system utilizes multiple clock oscillations for various timing purposes. Here is how the timing breaks down. 2 pulses from the oscillator produce 1 state. 6 of these states combine to generate 1 machine cycle. Depending on the instruction, the processor will need 1, 2, or 4 machine cycles for fetching the opcode and completing its execution. You will also see an AL signal available for each machine cycle. Whenever the system boots or needs to restart, the reset mechanism is engaged. A reset, or power on reset, must be active for at least 2 machine cycles, which corresponds to 24 oscillation periods. During this exact time frame, many of the internal registers are cleanly initialized. Let's look at the 4 major things that happen during a reset. First, the program counter, PC, is cleared to ensure the first instruction executed is fetched from address 0000H. Second, the stack pointer, SP, is initialized to 07H. Third, register bank number 0 is automatically selected. And fourth, all I/O ports output FFH. This circuit uses a resistor capacitor, RC, network to automatically generate a temporary logic high signal at the microcontroller's reset pin when power is first applied. How it works? The moment of power on. When the power supply plus 5 volts is initially turned on, the 10 microfarad capacitor is completely uncharged. In a DC circuit, an uncharged capacitor initially acts like a short circuit. Because of this, the entire plus 5 volts drops across the 8200 ohms resistor. This means the voltage at pin 9, the reset pin, immediately jumps to plus 5 volts, triggering the microcontroller's reset state. Now the charging phase, the reset delay. As time passes, the capacitor begins to charge. As it charges, it blocks more and more of the direct current, causing the voltage across the 8.2 kilo ohms resistor to drop exponentially. The time it takes for this voltage to drop is determined by the RC time constant. Is equal to 8200 ohms time 10 to the power minus 6 is equal to 82 milliseconds. This represents the time constant of an RC circuit calculated using resistance and capacitance. Returning to normal operation, the microcontroller requires the reset pin to be held high for at least 2 machine cycles to properly initialize its internal registers. The 82 milliseconds delay provided by this specific RC combination is more than enough time. Once the capacitor is sufficiently charged, the voltage at pin 9 drops below the logic high threshold, the reset state is released, and the microcontroller begins executing its program from memory address 0000 hex. Now let us understand the manual reset key. Warm boot. The schematic also features a push button labeled reset key in parallel with the capacitor. If the microcontroller is already running and you press this button, it creates a direct short across the capacitor, instantly discharging it. The reset pin is forced back to plus 5 volts. When you release the button, the capacitor begins charging again, recreating the necessary delay for a proper reset. Now, let's take a close look at exactly what happens inside the microcontroller during a reset. This table outlines the default values loaded into the internal registers the moment the system is powered on. To make this easy to digest, let's group these registers logically. First, you'll notice a clear pattern. A majority of the general control and math registers are completely cleared to 0. The accumulator, A, the B register, the 16-bit data pointer, DPTR, and the serial control register, SCON, all reset to 00 hex. The same goes for the timer registers, TCON, TMOD, and the high and low bytes for both timers 0 and 1. They all clear to 0, which effectively ensures that both timers are stopped when the system boots. Next, let's look at the input-output ports, P0, P1, P2, and P3. Unlike the previous group, these do not clear to 0. Instead, they all initialize to FF hex. This is a deliberate design choice. It configures all port pins as inputs, making them immediately ready to read external signals. Now, let's focus on 3 highly critical system registers: the program counter, the stack pointer, and the program status word. The program counter, or PC, resets to a full 16 bits of zeros. This is arguably the most important reset action, as it forces the CPU to fetch its very first instruction from memory address 0000H. The stack pointer, SP, resets to 00000111, which is 07H. Because the stack pointer increments before storing data, this ensures the system stack will safely start at address 08H onwards, right above the register banks. The program status word, PSW, resets to all zeros. As we discussed earlier, this specific action is what automatically selects register bank 0 as the default active bank. Finally, we have the interrupt and power control registers. In the interrupt enable, IE, and interrupt priority, IP, registers, you will see some excess. These represent undefined or unpredictable bits. However, the critical bits are cleared, ensuring that all interrupts are safely disabled upon startup. Similarly, the power control register, PCON, has unpredictable power-saving mode states initially, but configures timer 1 as the baud rate generator. Understanding these default states is essential, as it gives you a perfectly clean, predictable slate every time your program begins. Thank you for watching. I hope this session enhanced your understanding of the MCS 51 microcontrollers' internal architecture and memory mapping. Keep exploring and see you in the next lecture.